Alright, we got Unit 5. It's our last one. It's 18%. 18 multiple choice questions on the exam. This one is the hardest math of it all because it has the trig, vectors and vector addition in it, plus it also has the motion, magic physics formula stuff that we studied earlier, so special attention needed here. Let's start with equilibrium. Equilibrium is defined as the net force equal to 0. Go through and we put in our arrows. Weight, always straight down, we'll call it FMG. Then we have Fn, not quite as big as the FMG arrow, Fn. And in this particular problem, it's better to tilt the coordinate system like this. And then we can solve for the x component of the weight and the y component of the weight. However, in this entire problem, when you get done, you'll see here sum of forces in the x equals FMGX would be, we'll call it FMGX. FMGX would be the same thing as saying FMG, it's opposite, so sine of theta equals MA. And you'll notice that the M part is here and here. Therefore, the shortcut will be G sine theta. So if you want to know on a frictionless inclined plane what the acceleration is, we'll just say 9.8 times the sine of 20 degrees. And that will give it to you straight away, 3.35 meters per second squared. And I think you'll find that to be a lot easier than going through a lot of that trig. Let's jump over here to the top right. Projectile, that's the launched object. For example, in the ramps, the ball was the projectile. In the trebuchets, the clay is the projectile. Trajectory is the path of the projectile. And range is the distance it travels in the x. Distance in x. Put in our velocity vectors, the thing you want to remember is that the x stays the same all the way through while the y grows in the amount. At the beginning there's none, and it becomes more and more and more and more. So that when it lands, it has an overall resultant that is bigger than in the initial x because gravity has caused it to accelerate or pick up speed. Go ahead and we'll do some different examples here. I hit this pretty hard on the exam. It's the ramp scamper kind of stuff. Here we're trying to find Vx. We know the dx. You know, if we're thinking about a fraction, we already know that the top part of the fraction is 5. We just have to find t fall. Right, here's a little reminder for those that aren't using their formula sheet. 2d divided by g is how we come up with that. So when we're ready to find how long it takes to fall 25 meters, we just say 2 times 25 divided by 9.8 and we square root it. It's 2.25, 2.26 seconds. So our fraction is 5 over 2.26. And we get 2.21 for our Vx. Another one here, once again we got to find t fall. This time they're telling us V. We got to use this extension of it right here, which is Vx equals dx over t fall. Simple enough, right? So Vx times t fall would be dx. And that's what we want to know is dx. So t fall would be 50 times 2 divided by 9.8 square root. So we get 3.19 for t fall. So put that right there. And then Vx was 4. 4 times 3.19 will give us 12.76 for the distance. So that's it for the t-fall stuff. Let's look at some of the parabola stuff now. Full parabola, launched at an angle. Range equation, v naught squared sine 2 theta divided by g, in parentheses there. And t flight is 2 times the y component divided by g. Put in the arrows here. Remember, once again, the x will remain constant all the way through, while the y will do the changing here. So at the beginning we might have a lot of y, reduced, reduced, none. Now we go back the other direction a little bit more, back to the original amount. Key thing being that whatever it starts with, the resultant is the same resultant it will land with as long as the heights or elevations are the same. The angles will also be the same. So the angle I start with is the angle that I land with, theta. Alright, so let's try one then. Oh, max height, forgot about you. Vy naught squared divided by 2g. So in this problem, they've given us the initial velocity and the angle, and they would like us to find how long it's in the air for, and what the range is, and what the max height is, basically using these three equations. The first thing you should do is break it down, break down the 20 at 38. So that's sine and cosine, where the y component will be sine. So 20 sine 38. You can always use your vector calculator, right, and do it all in one step, but I'm old school. 20 cosine 38. So 12.3 and 5.8. So say 12.3, not 5, 15.8. Stop and see if it makes sense. Yes, it does. You know, it's less than 45, so the x component should be greater. Then what we can do is plug some things into these equations up here. Now remember, somebody took a lot of time in making these derived equations. You know, you can solve all these with the magic physics formulas. I'll just mention that one more time. For those that are trying to get by without having to memorize stuff. I find these to be the hardest to memorize. In fact, normally I just use the magic physics formulas when I solve these, but these get the job done also. So we'll say 2 times 12.3 and then divide by 9.8. We get 2.5. So that would be t-flight, 2.5. That's how long it's in the air for. Max height, we're going to use the y component again. For max height, we're going to take 12.3 and we're going to square it, and we're going to divide by 19.6. And we get 7.7 meters. For the range, when you plug it into the range equation, so we're going to say 20 squared times the sine of 2 times 38, and then we want to divide by 9.8, and that gives me a range of 39.6. What other angle will give the same range? Simply subtract from 90. So we'd say 90 minus 38, and we get 52 degrees. That's the other angle. Alright, derivative integral. This is really Unit 2 stuff, but I think I got to the point where I had 88 problems, and I just needed to come up with 2 more problems. So these will be the last 2 things you'll do, is try to make a derivative and integral. So if we create an acceleration time graph that's based on slopes, we can see here we have a positive slope, 0 slope, negative slope, 0 slope. So we're going to be, you can look at how steep this one is. This is quite a bit steeper than the other negative slope. And throughout here is 0, then a negative slope, not as steep, and then back to 0. So that's the acceleration. Positive, 0, negative acceleration, and then 0 again. In terms of area, you know, this is going to be positive area, positive area, positive area, positive area. So you'll keep tacking on here. So like maybe in this first time we might have an area like that, and then we have a lot of area here. So I'll kind of do that kind of thing. And then we have even more area, but you know, it's not quite as big a shape. And then once again, even more positive area. So we're just getting further and further away. We never even try to come back. So we're going to kind of curve into a straight line for constant speed. See, the speed is being held constant. Here I'm accelerating in a positive way, so I curve up. Now I have negative acceleration, but I'm still moving forward, similar to pressing the brake. It's kind of like slow down. So I curve. This is curved. This is straight, curved. You curve into this last line right there. Straight, straight, curve, curve. The inflection of the curve is in such a way that it's trying to approach a slope of 0, but it never gets there, right? It never gets down to a speed of 0, so the slope never gets to 0 either. It's just reduced. And so that's the derivative, or that's the integral, my fault. So this would be called the integral, and this is the derivative. This is based on area, this is based on slope. Alright, so, prepare those formula sheets. If you're not planning on using your formula sheet, maybe go through here and study the equations. There are quite a few. And I hope everybody does well, and stay hard.